Looking at the course page, homework number 2, MATLAB homework number 2, supposedly is now posted. I just ran into Josh in the hall. He'll be putting up MATLAB homework 2 momentarily. Okay, so both of these are up. Again, homework number 2 is based on trigonometry that we did this week that we're finishing today. It is due next Friday, 1 week from tomorrow by 5 p.m. Homework number 1, announcement still posted. MATLAB homework number 1 due tomorrow by 5 p.m. If you're not going to be on campus tomorrow, you can turn in homework today if you have it done. We have instructor TA office hours still going on after class today. All day tomorrow. There will be TAs in 280 Joshi. If you have any questions about the homework, the MATLAB, whatever it is. Questions, concerns before we move on? Yes?
And it's due in the Dropbox, right?
In the Dropbox. Your TA's name should be next to a slot in the Dropbox. Have we verified that? Yes, everybody found a TA there? Yes? Okay. So that should be good to go. And so, yep, just you can put them both in at once. The TAs will sort out, you know, the separate grade. You'll get 2 grades, 1 for each assignment.
Oh, yeah. And do that at 5?
By 5 p.m. You know, they reserve the right to just like collect the box at 5:01. Okay, so don't mess with the deadline. Like if you're working on this tomorrow afternoon, get it in there. Because some of the TAs might want to grade over the weekend, and they might actually only be hanging out here till 5 just so they can get the homework. So you never know. So we have kind of that firm homework deadline of 5 o'clock. If for some reason your homework is ever not complete, turn in whatever's completed by 5 o'clock so you can get some credit and go from there. Okay. Other questions, concerns about homework? Still plenty of time to crank that out, okay, before tomorrow. All right, let's see, what else? One other thing is we are getting caught up on videos, right? So here we go. We're going to get to the point. We had some initial startup to get going here. This is the lecture from day 1, the lecture from the end of the week, and maybe even this week. I'm hoping we're going to shoot to have both weeks' lecture videos posted by close of business at the end of the week, right? And so the idea is in the steady state here, whatever I lectured on during the week is up. The actual lecture's up there if you so choose to go back and watch a portion of it, or if you happen to have an excused absence or even an unexcused absence, you can still go back and get the material, and then that would be available to you for the entire next week, and the homework on that material is due that week. So that's our goal. Our distance guys are moving on it, and I think we're going to be okay. So we'll see by a close of business tomorrow. I think we'll see some more video go up. Okay, and then we're working on this one. We got some opening things going on iTunes U. You can click on that and see where we are. This one is more for the rest of the world. For you guys, the actual lecture of what I do in class here, that's all you need. Okay? Questions, concerns about course material? All right, so moving forward. So last time, we were talking about a one-link robot, okay, and we were talking about the idea that, you know, if I had a certain L and theta, you know, what would be the corresponding X and Y value, right? So it's my robot, I control the motor, I move it to where I want, where's the end point? Okay, what we want to do now is actually maybe the more typical problem, right, which is what we call the inverse problem. If you're controlling the robot, what you really want is you want the tip of the robot to be at a certain location. All right, so what you're actually given is the coordinates X and Y, and your job as the engineer is to write the algorithm to say, hey, I want to be at this point X, Y. What do I need to do with the motor, the angle, in order to make that happen? Okay, so doing the problem backwards is actually the more typical application of this. Okay, and so we'll call this the inverse problem of the one-link robot. Okay, and so essentially, okay, what we're talking about now is given the X and Y. Okay, what we want to find, okay, is the corresponding L and theta. Okay, and so of course these guys then are related by similar relationships, okay, except we've got to do them backwards. So here's X and Y, all right, and I got the motor at the center. Okay, and let's say that the link is at a particular point, okay, point P, X, Y. Okay, and now the question is, what's the L and what's the theta if what I know is the X and the Y? Okay, and so from last time, we talked about the trig functions that line these guys up, and we said that X is equal to L times the cosine theta. All right, and we said that Y is equal to L times the sine of theta. And so the question is, can I use those relationships to back out the L and the theta? And I would argue that we already did half of this problem when we said what happens if I square and add both of these equations, right? In fact, if I write this one underneath, it becomes more obvious, right? Square both sides and add them, you get x squared plus y squared is equal to what? I'll get L cosine theta, okay, we'll run through this again, quantity squared plus L sine theta, quantity squared, all right, and of course this guy is going to be an L squared in each term, right, and then I have a cosine squared theta plus a sine squared theta, and cosine squared plus sine squared is equal to what? Right, so that's it. So I can solve for L, right, and I get L is equal to the square root of x squared plus y squared, which is the Pythagorean theorem. All right, so essentially, getting the L, not too complicated. How about the theta? Any ideas on how I would get the theta? What could I do with these two equations, okay? One below the next, in order to solve for theta? So I could use an inverse sine function. Okay, that's true. Any other ideas?
Once you found L, then just know the x and y. You just plug them in and do its inverse.
Okay, so I could use an inverse sine. That would be using the y value in the L. Okay, how about this equation? Could I use that?
Inverse cosine.
I could use an inverse cosine. Is there any other option?
Inverse tan.
I could use an inverse tan. Okay, in fact, the nice thing about an inverse tan is that would be one where I could do independent of this, right? Whether or not I have an L, what can I do to these two equations to use an inverse tan? Yeah, I could divide them, right? Because isn't the tangent of theta equal to y divided by x, and the L will cancel right out of that, right? So it's L sine theta divided by L cosine theta. Okay, and so, you know, that's it, right? So the L cancels right out of that. Okay, and so I could just use the y and the x values directly, okay, without having an intermediate answer for L. So theta would be the tangent function, right, inverse, angle whose tangent is y divided by x, okay, tan minus 1. Okay, incidentally, emphasizing this notation, this is not the tangent of y over x to the negative 1 power. Okay, this is tan minus 1, and this could be confusing, right? Because when we write sine squared and cosine squared, okay, we put the 2 over here. That means the cosine function quantity squared, the sine function quantity squared. This is the notation. Inverse minus 1 here does not mean the tangent function 1 over that. Okay, it means, say it out in words, theta, tan minus 1 means is the angle whose tangent is y over x. Okay, and so that's the minus 1. Questions on that? All right, so I got two answers, right? I can get the L, Pythagorean theorem, directly from the x and y, square root x squared plus y squared. I can get the theta by just taking the inverse tangent function. Okay, so this is inverse tangent. okay, also known as the arctangent, okay, function. All right, so what I'd like to do is point out some things about the inverse tangent that can be a little problematic from a computational standpoint, okay, and it's something we have to deal with all the time in engineering, really important to understand. Okay, so let's take these ideas, okay, and see if we can apply these formulas to some specific cases. So for example, okay, given an xy value, let's look at some trivial cases, see whether or not the formulas work. Okay, so for example, xy, let's say it is 1, 0, and I want to find the L and I want to find the theta. Okay, then first of all, where's this thing located on the xy coordinate system? Straight up and down on the y-axis? Horizontal on the x-axis, right? X is equal to 1, y is equal to 0. So here's the endpoint, right? That's what we mean, 1, 0. Okay, and so this would be the link is just laying down here on the x-axis. Okay, so the nice thing about this, right, is I'm trying to find the L and the theta. So this, again, these trivial cases, I can do these things by inspection, right? Just by looking at the location. Okay, and you tell me, L is equal to what?
1.
Yeah, L would be equal to 1. Okay, and how about theta? Yeah, theta is the angle that the link makes with the x-axis, right? And so if I am laying down on the x-axis, I have no angle. So theta is 0. What about the formulas? Right, I ought to be able to look at the formulas and see if they work. Shouldn't L be the square root x squared plus y squared? We can plug in the numbers. Square root, x is 1, y is 0. So this is 1 squared plus 0 squared. That gives me what? Square root of 1 is still 1. Great, so that formula works. How about this guy? Theta is equal to tan minus 1 y divided by x. Tan minus 1, the y value, 0. The x value is 1. How do I evaluate a tan minus 1? Like what if I said, find tan minus 1 of what? 3.476. How would I do that? Calculator, right? All right, so pull out your calculators. Smartphones, whatever, something that's got a scientific calculator. Hey, let's make sure the calculator works on these guys. We're going to use calculators on every exam in here. We have to make sure they give us the answers we want. So run this guy in your calculator. Theta is tan minus 1 of 0 divided by 1. What do you get? 0. All right, so seems like the calculator works pretty well. Okay, and the answer is theta equals 0. The inspection seems to line up pretty well, okay, with the formulas. All right, well, how about this case? What if I have the opposite? So the xy value, okay, instead of 1, 0, okay, let's say x is 0 and y is 1. 0, 1. Where's this guy? So the endpoint, right? Motor's here. The endpoint for x is 0. The y value is 1. So this would be straight up and down, right now on the y-axis. Right? I know the coordinates. This is 0, 1. I know the length is L. And this is the theta I'm trying to find. Can I do this one by inspection? Sure. Right? By inspection, what's the L value? Yeah, the L value is 1. Okay. And how about the theta? Yeah, it looks like 90 degrees or pi over 2 radians. Okay, 90 degrees pi over 2 radians. Okay. Let's try the formula. L is supposed to be the square root x squared plus y squared. X is 0, that's 0 squared, plus y squared, 1 squared. Any problem with that? Square root of 1 squared is still 1. How about this guy? Theta is tan minus 1, y divided by x. Somebody run this one in their calculator.
You can't divide by 0.
Can't divide by 0.
That still gives me a plus minus pi over 2.
Do we have a problem here?
Yep. Mine gives me plus minus pi.
Okay, so he's got a calculator that's smart enough to know, right? When you entered it in there, is it showing it symbolically in your calculator? Yeah, so it's looking at the numerator and denominator, and it's programmed to understand what's going on there. Excellent. Anybody else? Regular scientific calculator? Can you compute this? Probably not. You know,
Divided by 0.
yeah.
Isn't that impossible?
I don't know. Is it impossible to have the link right there? That's a great question, right? All right, so let's think about this. Think about this from an engineering standpoint, okay? What's 0?
Nothing. Nothing. The midpoint between positive and negative.
Okay. So this number's 1, right? What's a number that's pretty much 0? All right, point with a bunch of zeros. Do I need a lot of zeros?
Oh.
Well, you guys are engineers, right? Put a number in here. 1 divided by something. Something close to 0. Stick a number in.
0.01.
All right, so he's doing 0.01. So 1 over 0.01 is how much? 100, right? Okay, so what's the arctangent of 100? Punch it. Arctangent of 100. 89.4. That's pretty close, right? What if I said I want the answer to 3 significant digits? 0.01's not going to do it. What about 0.001? That's pretty close to 0. Arctangent of 1,000 is what? I like that better. How about tan minus 1, 1 divided by 0.001, right? And so you get there, as close as you can compute, you said what? 89.9 degrees. All right, close enough. All right, so one thing to realize is that, yeah, physically I can be there, right? The arctangent function is the division of 2 things, right? When one of them is 0, you're going to have a numerical issue, okay? It doesn't mean you can't physically be in that location, right? And in fact, the sheet right here, right, the 1 page of trigonometry I handed out, the authors of your calculus book said this is the stuff that you really got to have from trigonometry. You can take a look at the plots of the function, right? And so the plots of the function, you have these vertical asymptotes on the tangent function, okay? And so these are the vertical asymptotes, right? When I approach 90 degrees, okay, then I get a problem, right? The division goes to infinity. What about if I was down here at the other end? It's still a 90-degree angle. It's a negative 90-degree angle, right? But I've got the same problem. The x leg is still 0. All right, so that's one issue. let me point out another issue. Let's put some in that aren't trivial. Okay. Let's think about when I want to find the angle, and maybe the reference angle is the same, but the quadrant's not. Okay? So let's think about two possible cases. So let's consider two cases of the inverse problem. Okay? Number one, relatively straightforward. What if I said that the tip of the robot was located same x and y coordinates, okay, in the first quadrant right here. So xy is equal to, we'll use this, 1 over root 2, 1 over root 2. By the way, give me a decimal for 1 over root 2. Is that right?
0.7071067.
All right, about 0.707. Okay, so each one of these is 0.7. Okay, I want to find the L and the theta. This special case, okay, I could do this by inspection also, right? Because when I have a triangle and the sides are equal, then the angle is how much? 45 degrees. Great. So even this one, I could do basically by inspection. I could recognize that this is a 45-45. And if I remember from geometry, it's a 1 root 2. So the length of this is going to be what? 1 root 2. So it's root 2 times this, right? Root 2 times 1 over root 2 is 1. Okay, so that's the inspection. But hey, let's say that those aren't exactly the same numbers. I want to try the formula. Let's see if the formula works. L is the square root, x squared plus y squared, right? Let's put the numbers in, see what we get. We get 1 over root 2 squared plus 1 over root 2 squared. I take the square root of that. 1 over root 2 squared is how much? This is a half, right? Plus another half. Square root of 1 gives me 1. No problem there. Let's see what the calculator says. Theta, tan minus 1, right? Y divided by x. So it's going to be tan minus 1, and I've got the y, 1 over root 2, divided by the x, 1 over root 2. Run that in your calculator. Tell me what you get. Pi over 4. Calculator, somebody do it in degree mode. Right, when you do an inverse tangent function on the calculator, you got more than one choice for the mode of the answer. Right, you can put your calculator in degree mode. If it's in degree mode and you do a tan minus 1, you get what? 45 degrees. And if you have it in radian mode, yeah, you get some number like that. A decimal on a scientific calculator, 0.7853. That number would be pi over 4. If you have a smart calculator that does symbolics, maybe it says pi over 4. Okay, so this is pi over 4 radians. All right, so you look at that and say, great, you know, I could really do any value of x and y. I got formulas. I can just plug this guy on my calculator. I'm golden. Well, what if I just move the thing over to the third quadrant? Okay, so let's take a look now and see how well this works if I move the quadrant. Okay, so now let's say the link is over here. Okay, and so if I am over here in the third quadrant, here's the L. Okay. The theta is this way, right? Looks to be a negative angle. Okay, and let's say this time that the x and y value, okay, are what? Both negative numbers. Minus 1 over root 2, minus 1 over root 2. Let's try the formulas. L is supposed to be equal to the square root, x squared plus y squared. So this is the square root, negative 1 over root 2 squared, plus negative 1 over root 2 squared. What happens to the negative when I square that term? Goes away, right? So both of these negatives go away when I square it. So I got no problem here. I still end up with the same answer, 1. What does my calculator say? Tan minus 1, y divided by x. This is tan minus 1 of negative 1 over root 2 divided by negative 1 over root 2. Let's plug that in the calculator. Tell me what it spits out. (45 degrees). All right, this is the calculator. Does that angle look like 45 degrees to you? Right? Wrong answer. Okay, so immediately you seem to have a little bit of a problem here, okay, because clearly I want to be able to move this thing around the entire plane, right? I don't want to just live in the first quadrant. In general, when I compute a tan minus 1 operation, okay, whether it is on a calculator or in a computer program, right, tan minus 1 is a function that is defined, okay, that has a range of values in either the first or fourth quadrants. When I take the tan minus 1, the angle whose tangent is a certain number, if that's a positive number, the angle it gives me is between 0 and 90 degrees. If it's a negative number, the angle it gives me is between 0 and negative 90 degrees. It will spit back an acute value of an angle, plus or minus, and that's it. I'm missing the entire other half of the plane over here. So, one thing to do is look at it and say, well, that's fine, but I can see where it is, right? The calculator is really giving me what here? It's giving me this reference angle, say alpha. Okay, that's the 45. So you can say, well, I can look at it and I can see where it is. And that's fine to understand that. But as an engineer, you're going to have some code. You know, you're going to have some MATLAB code or something that is trying to control the motor. And just because if you sketched it all out, you could see where it was, the numbers need to be able to tell it where it needs to go. And 45 degrees is not where this is. 45 degrees would put it over here. Okay, so it's a real issue. You have to be able to have an inverse tangent function that could take care of any one of the quadrants. Okay, this is the same issue, by the way, if you've had physics and you've done some vectors and things before. Same issue. You got to know which way things are pointing. First quadrant, second, third, or fourth, not just half the picture. Okay, and so the question is, what do I do about that? Okay, and what do you think? If I want to keep track of the quadrant, what is it that I really need to keep track of here, given the x and y values? Right, because that's what I was given, the x and y values of the end of the robot. If I want to know what quadrant it's in, what am I looking at on those x and y values? The signs, S-I-G-N, right? And the problem with the tan minus 1 is when I divide the two numbers here, the sign cancels out. So I lost the information. The information's gone. Okay, so what I need is I need a function that keeps track independently of the signs. The sign S-I-G-N of the numerator, right, the sign of the y value, and the sign of the x value. Right, and it's right where we left off last time, that depending upon the quadrant, I have a different sign, S-I-G-N, right? And it's because is x to the right or left, right? And is y up or down. So if I keep track of the sign, S-I-G-N, okay, then I'll know exactly which quadrant I'm in. Okay, so it turns out that we have a function for that, okay, and that is in MATLAB, okay, built-in function. Okay, and so that's this guy. We call it ATAN2. So you can do an ATAN, arctangent, in MATLAB, give you the same problem as your calculator. Or you can do an ATAN2. The inputs are y comma x. So it's not y divided by x. ATAN2 is a function, and the arguments are the y and the x. So that's the way you write it. Okay, and this is what's called the 4-quadrant, okay, arctangent. Okay, really, a tan 4 might have made more sense, right? 4 quadrants. It's a tan 2, meaning there's more than one a tan function. A tan is tan minus 1. A tan 2 means not just the number in here, but separate values for y and x. Okay, and so here's the idea. This thing computes, okay, tan minus 1, okay, but keeps track, okay, of the sign, right, the signs of y and x to locate, right, the quadrant. That's the idea. Okay, and so when you do that, you can assign the corresponding value, right? Because, for example, if I know in this case that when I do the tan minus 1, I get 45 degrees, and I know that answer is a third quadrant, okay, answer right here. Okay, then what the calculator is returning is this value, the first quadrant answer. So if my program said, well, I know I'm over here in the third quadrant, how do I get from what the calculator would give me right here, how do I get from here over to here? Add how much? I add 180 degrees, right? Or I add pi. Okay, and in fact, anytime MATLAB, you do a program and you say, give me an angle, and it spits out the angle, what units do you think is on the angle? Radians. Okay, so you add pi to it. So the point is, I can use a tan minus 1 function that I know is going to give me 45. But if I know, wait a minute, y is negative, x is negative, well, in that case, I'll take the answer I get from tan minus 1, and I'll add pi radians. Okay, and that'll get me in the right spot. So as long as you keep track of the signs of y and x, that'll locate the quadrant, and you can go. Okay, and so the point is, this returns values in the entire range. So it returns values, okay, in the range minus pi is less than or equal to theta, less than or equal to pi. Okay, so think about that. Negative pi all the way to positive pi. So it will give you a number that is either plus or minus, but instead of a number bounded between plus and minus 90 degrees, it's bounded between plus or minus pi radians. So it's the entire unit circle. You guys with me? Great. So what we will use repeatedly in this class is when we are doing an inverse tangent in order to find a physical location, okay, which we do in vectors, which we do in some trigonometry problems, which we'll even do in a complex number kind of problem, where we need to keep track of all 4 quadrants. I will use this notation even for handwritten problems, right? So I won't say tan minus 1, I'll say a tan 2, just to emphasize, right, that what we're doing is a tan minus 1, but we are keeping track of the quadrant. So when we report an answer, the answer we report will be in the correct quadrant. Okay? All right, so let's take a look at this. Let's do a new example, okay, where the numbers can't be gotten by inspection. Okay. And what we'll do is we'll solve it 3 different ways. Okay? Basically doing the a tan 2 on our own, okay, from the trigonometry, and then finally kind of invoking MATLAB to see. Okay, so let's say that x and y are these 2 values, minus 0.5 and 0.25. Okay. The problem is to find the L and the theta. Okay. And so, first of all, what quadrant am I in? Second quadrant, right? It is 1, 2, 3, 4. If I have a negative value of x, I'm to the left of the axis, positive value of y, I'm up, so I'm over here. Not a bad idea to draw it sort of to scale. Okay, so the x is more than the y, all right? So if these are each 0.25, then that'd be about here. Okay, and so this is what I'm looking at. Okay, and so what I would like to know is what is the corresponding angle theta, right? That is the value of theta that's bounded between 0 and pi. Okay, it looks like that. Okay, and of course, coordinates, minus 0.5, 0.25. That means the two legs here, 0.25 is the vertical leg, okay, and 0.5 is the horizontal leg, and of course it's a negative number. And then finally, L is the length of the link. All right, so first of all, to calculate L. I don't have any problem, no matter what quadrant I'm in, right, to calculate the length, because I'm squaring and adding. Any kind of sign I would have cancels right out, right? And I get a positive number always for the L. So it's the square root x squared plus y squared. So we can plug the number in, see what we get. So it's minus 0.5 squared plus y squared, 0.25 squared. Okay, and somebody run those numbers for me.
A long decimal.
Give me 3 digits.
Okay.
What is it? 559. Okay, great. So that's the L. Okay, and incidentally, we'd really want to have dimensions on this. So let's just say that this is inches and this is inches. If that were true, then L would be in inches. And we'll use the double quotation marks. That's a common symbol for inches that we use. All right, so how about the theta? Let's try this guy on the calculator. Tan minus 1, right? Y divided by x. Is this going to work? Tan minus 1, y value, 0.25, x value, minus 0.5. Somebody run that for me. One more time, negative what?
26.56.
Negative 26.56, is that radians? Degrees. What is that in radians?
Negative 1.463, 464.
Negative 0.464 radians. Okay, so first of all, if I punch the calculator, that's what it gives me. It gives me a negative number. Is this angle negative? Okay, so right away I know that the calculator returns an answer in one of these two quadrants. So the one it's giving me is over here, right? It's giving me this angle, right, which is 26.56 degrees negative. So first of all, I got to recognize that this is wrong. Okay? So wrong answer. So I got to correct this a couple of ways. I can do it from the geometry. Okay, let's think about really a couple different methods. Okay, I can go ahead and use the calculator. Okay, and if I use the calculator, how will I go from the calculator answer to here? What do I do? I got to add 180 degrees, right? Or in radians, I would add pi. Okay, so number one is I could use the calculator, okay, and I can add 180 degrees because I realize the calculator gives me the wrong answer, okay, the wrong quadrant. So in this case, its theta is going to be tan minus 1, right, y divided by x, 0.25 divided by minus 0.5, and then I'm going to add to that 180 degrees. Somebody run that for me. What? 153.4 degrees. Does that pass the sanity check looking at it there? Sure, right? I mean, it is, the y is a little less than the x, so I'm more than halfway through the quadrant. 180 would get me there. Passes the sanity check. Okay, great. 153.4. Another method you could do, also really by hand, okay, method number 2, is I could say, you know what? Anytime I do a tan minus 1 on my calculator, I'm not going to use the real values of y and x. I'm going to come over here, and I'm always just going to use a reference angle, alpha. And I'm going to look at the picture and say, well, given the alpha, the real angle would be what? Suppose I forget the signs, S-I-G-N, and I just find the alpha. How would I get the right answer here? I'd take 180 and I would subtract the alpha, right? So similar to what we just did, but actually a slightly different thought process, right? The other one puts me in the wrong quadrant, and I connect it over here by adding 180. This one's like, no, forget that. I'm just going to do the triangle, and then I'll look at where I am and say I'll subtract that. Okay, so method number 2 is essentially to ignore the signs, okay, and use the reference angle. Okay, and so if I do that, okay, how would I get the right answer? Well, theta would be, using the reference angle, 180 degrees minus alpha. Okay, my reference angle alpha. Alpha is the tan minus 1. So theta is 180 degrees minus tan minus 1, where I ignore the signs. So I'm just going to put the legs of the triangle, 0.25, 0.5. Okay, and so now, if you run that on your calculator, you get what? Same thing, right? 153.4 degrees, because the tan minus 1 is now a positive 26.56. Okay, so these are really two separate thought processes you can use to arrive at the same answer, given that you're looking at the picture. Okay, so the problem again is, as an engineer, I want to automate my robot. I want this thing to be able to move around, told by a computer. I'm not going to stop every time and ask the question where I am and do this manual correction like we're doing here. Okay, so you got to make a distinction. What's your thought process if you're solving a problem by hand, a vector problem or whatever? Well, it's one of these processes that you would use. If I'm going to write code to do something in an automated way, I probably need to have a function that takes care of that. Okay, and so let's come over here and try MATLAB. And so what I need is I need to try an a tan 2 and see if it spits out the right answer. So I want a theta equal to, I'm going to pull that thing down, so I'll move it here. Theta is equal to a tan 2, right, y comma x. So again, using the actual numbers for x and y, 0.25, negative 0.5. Okay, and so let's fire that up on MATLAB here and see what we get. I need a mechanical engineering student to design for me the super turbo high-powered screen, okay, because I don't have the patience for that guy. All right, so let's see. So here's MATLAB. Okay, and so let's just try this out to see if it works. So it would be a tan 2, okay, and then it's y comma x. So the y value, now this is kind of nice, right? When you start typing a function in MATLAB, it'll immediately spit this out and say, hey, do you want help on this? You could click on it, it'll bring you to the whole like background description of the function. Okay, so when you're messing around with MATLAB, if you ever want to do something in MATLAB and you're not sure what it would be, like, hey, is there a function for this? Just pretend that you work for the MathWorks over here and you had to make it up yourself. Okay, because most of the function names are basically what you would come up with on your own. So you start typing it and bam, you'll find it right there in the help. Okay, and so that's it. A tan 2, 0.25, comma, negative 0.5. Okay, and the answer to this is supposed to be what? It's behind here now. 153.4 degrees, right? Uh-oh. There is no a tan d. This is a good point, right? So when you do a sine of theta, cosine theta, tangent of theta, the argument is an angle, right? If you don't tell it anything, that angle better be radians. If you like degrees, you can use a sine d, a cos d, a tan d. Doesn't work that way with the atan function. Okay, the atan function always returns an angle in radians. Okay, and so if you want to correct for this, you could retype what you had and convert it, or in MATLAB, if you hit the up arrow, it'll automatically put the last line that you did, which is nice. And if I want to convert, I'm going to multiply this by what? Pi over 180. So if you're writing MATLAB and you need a number for pi, what are you going to call it? Pi. Let's try that. All right, pi. Pi divided by 180. Oops. Is that right? Is this right? Do I multiply by pi over 180? Atan 2 gives me radians, right? 180 over pi. Okay, I just typed what you told me. 180 divided by pi. There we go. 153.4. Okay? So that's it. So a couple things to note again. Anytime you want to locate something physically in 4 quadrants, always think of an atan 2. Keeps track of the signs, right, of x and y separately. It knows the quadrants. Okay? That's it. It always returns an answer in radians. If you want to work in degrees, that's fine, but you got to build the conversion right into your code. Question?
So I know that MATLAB is basically coding these situations or problems.
Yep.
What do we turn in? Do we print out or something?
Well, so in your MATLAB homework, it says at the end what to turn in. Okay, it's actually a section says what to turn in. So, so depending upon the assignment, you'll turn in the command window, a script file, whatever it says for what to turn in. Is that clear?
Yeah, it's clear. This thing's slow.
I know. That's what I said. I need a turbo power. All right, great. So again, I do this, right? And the key thing is I had to multiply this times 180 divided by pi, right? And that's when I got theta is 153.4 degrees. Okay, got to have the conversion factor in there. All right, so that's it for the one-link robot. I want to talk now about what happens when I start adding another link. So this is the idea of the two-link robot, which is quite a bit more interesting than the one-link robot. Okay, and so the idea of the two-link robot is now, if I want to locate various points in space, right, beyond just being on a circle. That's the problem with the one-link robot. I'm stuck with just a circle. I get a lot more options if I add another link. Okay? Now, depending upon the lengths of those links, it can limit what the options are. Okay, so let's define this as general as possible. 2 different links, okay, that in general might have 2 different lengths. Okay, and so I'll have a first link over here. We'll call that L1. And then relative to that, we'll have the second link over here. Okay, and the length of that guy is L2. Okay, and I'm going to define the angles such that theta 1 is defined like theta for the one-link robot. But theta 2 is actually relative to the first link. Okay, now, I don't have to do that. Okay, it's up to me to define this the way I want. Okay, but in the end, I got to use these definitions to locate the point, x, y. Okay. Somebody give me a practical reason. If I'm designing a robot, okay, say I work at Motoman, right, and it's got more than one link. Every one of these links is a joint, right, and the joint at the corners is controlled by a motor. Why would I want to define the angles, theta 2, for example, relative to the first link? What do you think? Because I mean, I could define these guys so that they're always relative to the x-axis, right?
You're going to get it to dxy only if you know where theta 1 is.
Yeah, but that's true no matter how I define it, right? In other words, I could come over here and do a horizontal, and just define theta 2 also as an absolute angle relative to the horizontal. I could do that. So as an engineer, why might I want to define it this way?
Yeah, it's a relationship between the two arms, and that's what you're trying to get. I mean, like, you're moving the second link in relation to the first link.
Okay, so how am I doing that literally? These are links, and these guys are what? Motors. So I'm controlling the motor right here, right? So, you know, in general, we're talking about a dynamics problem. So we're thinking about this in a static way. I'm going to move to a certain angle. But I'm actually controlling an angular velocity, right? Or I'm rotating this a certain distance, right? Total number of radians. Okay, and so the bottom line is, as the first link moves, the motor at this joint moves with it, right? So you want to think about this as separately controlling these two motors. I move link 1, and now I've got a location of the tip, and then now I move the second link. By controlling that motor, the motion I get will be relative to where I am. Okay, so I can always compensate for that. I could have defined it as horizontal, but then I'd always have to do a calculation to essentially subtract off this one in order to get the relative angle. Okay, so it makes more sense to define it in terms of relative to the first link because what I'm controlling is this motor. Okay, that's the idea. All right, great. So first question, the forward problem. Given L1 and L2, how do I find the point? Given L1, right, L2, and the angles, theta 1 and theta 2, how do I find the location? Find x and y. Well, this isn't too bad. I can just kind of lay it out. Let's say it's in the first quadrant like that. Okay, and so we'll just draw the other ones real small. Okay, let's see if we can lay out kind of the geometry of this here. Okay, and we'll blow it up a little bit so we can add some dimensions and things. Okay, so let's say that, you know, here's the stick figure version of it. This is L1, L2. Make sure this is clear. This is theta 2. This is theta 1. Okay, in order to get the final xy value, okay, what I'm talking about is if I drop the perpendicular straight down there, okay, I'm trying to find these coordinates, right? P, x, comma, y. So here's the way I would think about it. I got two different links. Can I just look at them one at a time? So look at the first link. If I think about the first link as its own right triangle, then the adjacent side, let me call that x1, goes with link 1. And if I look at link 2, can I come straight over like this? Okay. And this distance now here is x2. Similarly, first link, vertical leg, we can call that guy y1. If I project it over to here, this is still y1. And then the opposite side on link 2, its own triangle, I can call that y2. So how is x1 and x2 related to the total value x? Any thoughts? You just add them up, right? In other words, the total x coordinate by inspection, x is x1 plus x2, right? So here's the thing. What I know is L1, L2, theta 1, theta 2. If I know L1 and theta 1, can I get x1?
Yeah.
Sure. So x is, what's x1?
Cosine of theta 1 times
Yeah, it's the hypotenuse L1, cosine theta 1, right? So it's L1 cosine theta 1, that's the first term. How about x2? Right? x2 is this horizontal leg right here. Well, the hypotenuse is L2, right? I want this leg. Cosine theta 2? Oh, because this guy is what? This is still theta 1, right? So I need to add these two angles to get the entire thing. All right, so this is times the cosine of the sum, theta 1 plus theta 2. Okay? And so we'll be clear, we'll use parentheses on both. So for the second link, I got to get the total angle relative to the horizontal to do this calculation. Okay? If I would have defined theta 2 as the absolute angle, I wouldn't have to do that. But from a practical standpoint, it'd be harder to control the motor. All right? The motor is the relative theta 2. You guys with me? All right, how about the y value? Right? By inspection, the total y is what? Got to add them up. y1 plus y2. And so y1, opposite leg on the first link, is what? L1 times the sine of theta 1. Good. How about y2, opposite leg of the second link? Yeah, it's L2, and it's the same story, right? This interior angle, right, in the right triangle for the second link, that interior angle is the sum of the two. So it's the sine now of the sum, theta 1 plus theta 2. So apparently, I've got formulas now that are going to take care of the x and y values no matter where I am. All right, so let's try this for a case or two. I've got a bunch of cases of this in the notes, but let me try it for a couple not completely trivial cases. Okay, what if, for example, right, let's say theta 1 is 90 degrees, theta 2 is negative 90 degrees. Okay, now keep in mind how theta 1 and theta 2 are defined according to this picture. If we were on exam number 1, okay, and we were given this, and we said sketch the robot, okay, in the plane, where is it? First, second, third, or fourth quadrant? Where's the end point? So the origin's always here. Here's the way you want to think about these problems, right? You're controlling the motors. I can move the first link, then I can move the second link. So let's move the first link first. Theta 1 is 90 degrees, going to put me where? All right, straight up and down. Okay, so I'll go right to here with my theta 1, okay, right here like that. Theta 1, 90 degrees. Okay, this is L1, whatever the number is. Theta 2, negative 90 degrees. So the link that's at the end here, right, now goes negative 90. Where's that put it? So this would be it if it went nowhere, right? Now it goes negative 90, which means what way? Clockwise or counterclockwise? Negative angle is clockwise or counterclockwise? Clockwise, right? Positive angles always defined, right, as counterclockwise rotation from x towards y. So if this is negative, okay, it goes the other way. All right, so now this thing is going to end up sticking straight out this way, okay, like that, L2. Okay, and so here's the end point, right, coordinates x, y, and of course this is the angle, theta 2 minus 90 degrees. Okay, so first of all, understanding physically where this is, and you'll mess around with these also in lab next week. We've got little 2-link robots that you can measure all your trig relationships. Okay, and you'll get a physical feel, but really we want to be able to plug formulas and have them work. Okay, so for a case like this, can I do it just by inspection? XY, by looking at it, is going to be what? Yeah, right. X, by definition, is the distance from the y-axis. Looking at the picture, L2, right? So this is going to be L2. And y is the distance from the x-axis. Looking at the picture, L1. All right, great. So I can do that without formulas. Let's double check that these formulas work. I got positive angles, negative angles. These should work. Okay, according to the formulas here, okay, x is supposed to equal L1 cosine theta 1 plus L2 times the cosine of the sum, theta 1 plus theta 2. Let's plug in the numbers. L1 cosine theta 1, that's 90 degrees, plus L2 cosine of the sum, 90 degrees plus negative 90 degrees. What's the cosine of 90 degrees? Cosine of 90 is how much? 0. What's 90 plus negative 90? 0. What's the cosine of 0? 1. L1 times 0 plus L2 times 1, x equals L2. Right? And that passes the inspection argument. How about the y value? All right, y should be L1 times the sine, right? Times the sine of theta 1 plus L2 times the sine of the sum, theta 1 plus theta 2. Let's plug our numbers. L1 sine of theta 1, that's the sine of 90 degrees, plus L2 times the sine of the sum, 90 degrees plus minus 90 degrees. So the question is, what is the sine of 90 degrees?
1.
This is 1. What's the sine of 0 degrees? 0. So I get L1 times 1 plus L2 times 0. I get y is equal to L1. Check. All right, so turns out because the sine of an angle, right, no matter what the angle is, plus or minus, no matter how you define the angle, first quadrant, second quadrant, third quadrant, fourth quadrant, when I go forward, I get a unique answer, right? The sine of 135 degrees over here is an answer, okay? And the fact that it's over here in this quadrant doesn't give me a problem, right? The cosine of 135 going to give me what? Give me a negative number over there, right? So it takes care of itself. So the sines, SIGN, and everything else, when I'm going forward with these relationships, these should work for any configuration all the time. I got a formula, I can plug it. Okay, so that's nice. Here's the problem. I'm designing an automation system and I've got a robot. I'm not just saying, let me make the theta equal to this number. Where does the tip end up? It's the inverse problem, right? It's saying I've got to pick this thing that's located here. What do I tell the motor to do, right? That's the question. So the real application of this is not given L and theta, find x and y. The real application is given x, y, where do I need to put the robot? How do I control the motors? The inverse problem. Okay? And so the best way to do the inverse problem here is just straight out by example. Okay, there is no general formula like what we just did here for the forward problem. Okay, and so let's do an inverse case where we can use some laws of trigonometry to back out the values. So, inverse problem. Okay, and so given, okay, essentially the point, right, the coordinate pxy, and it's my robot, Okay, so I know the lengths of the links, L1 and L2. What I want to find is I want to find the corresponding angles, theta 1 and theta 2. All right, so the L1 and L2, it's my robot. I designed it, so I know the lengths of the links. I know what point I have to pick. The question is, what angle do I tell the motor to do? Okay, so let's use a specific example here. Okay, we'll put some numbers in. Let's say the point XY is 12, 6. Okay, and just for simplicity, I'll use equal lengths of the links. L1, L2 equal to 5 root 2. Okay, so the 5 root 2, we pick that number, simplifies a little of the math as we move forward. In general, you want to be able to do what we're doing here for any values of L1 and L2. Okay, and so in general they won't be equal, and in fact the one already assigned for homework, you got a couple of these, they're not equal. Okay, and the reason I say that is when you have equal lengths of links, you can take some shortcuts in the trigonometry if you take advantage of that. Okay, we're not going to take shortcuts. We just got equal lengths for simplicity of numbers. Okay, so moving forward here. First of all, 12, 6 is in which quadrant? First quadrant. So I'm blowing this thing up and we're looking just at the first quadrant location here. Okay, and so I want to find the two angles when I'm at 12 and 6. Not a bad idea to use, semi to scale kind of drawings when you do this so you can get a sanity check. So if this is 12, then these tick marks are each 6. And so, this is 6 over here. That means the end point of this guy is going to be right about here. Okay, and the start point is over there. Okay, and so this is 6, this is 6, this is 12. Okay, this is the point. Pxy is equal to 6, 12. 12, 6, sorry. X is 12, Y is 6. Okay, and so, how do I have equal links that connect up to this? The way you would do this if you ever did any drafting or something, you could take a compass, right, and set the length, and you could put it here, and you could draw arcs and see where they intersect. When the lengths are equal, you can kind of come in here like this. This is my method. Okay, and say, where do I put the dot so I'm about equidistant? And to me, the dot is right about here. Okay, so I've got these two links. They look about like this. One to there, and then a change in angle up to that one. Okay, and so what I'm trying to find here is two different angles. Theta 2, the relative angle, okay, from link 1 to link 2. And this guy here, which looks to be a pretty small angle, theta 1. Okay, and I know the length of the sides. This is 5 root 2. And this guy here is 5 root 2. Okay, and again, the end point of this thing is at 12, 6. Okay, so I can think about it that way. Okay, as 6 and 12 are, this thing's in a box. That's 6 and 12. All right, so here's the idea. When you try and solve a problem like this, okay, what you need to do essentially to find these angles, okay, is you're going to have to solve the entire triangle that makes up these two links as the sides. Okay, and so here's what I want to draw for you in a separate kind of plane here. Let me draw the whole thing again, where I have the 6 and the 12. This is 6, this is 12. Okay, this is my location in between here, like this, and say like this. Okay, and what I'm trying to solve is this non-right triangle right there. Okay, that's what I want. All right, and so again, the lengths of these edges, each one of these, 5 root 2, 5 root 2. Okay, and ultimately, I need an answer for this guy, theta 2, and I need an answer for this guy over here, theta 1. Okay, now, if the three solid lines here, if I knew all of the angles and all of the lengths, could I get theta 1 and theta 2? Give me a strategy. I don't need equations, just in words. If I knew this angle, right, the obtuse angle here, how would I get theta 2? You're jumping ahead to how do I get this angle. Say I have the answer, how do I get theta 2?
180 minus
Yeah, it's just right. Theta 2 is the relative angle, so it's just related to 180. So in fact, this angle here is 180 minus theta 2. Okay, that is the obtuse angle. 180 minus theta 2. What about this guy? If I had this little angle here, let me call that alpha. If I had this little acute angle alpha, how would I get theta 1?
Minus the theta
All right, if this little angle here is alpha, how would I get theta 1? Theta 1 minus alpha is theta 1?
90 minus alpha.
90 minus alpha? These two have to add to 90? What if I knew this total angle here? How would I get the total angle there?
Minus 90 minus the angle on the top of that line.
Well, this is a whole nother angle, right? Turns out, if the lengths of the links are equal, this one and this is the same, but that's not generally true. Okay, so stay away from that shortcut. What do you think? Okay, so look, these two together, alpha plus theta 1, right? That angle, isn't it true that the tangent, right, of theta 1 plus alpha, right, is equal to what? 6/12, right? So if I knew the alpha, there's only one unknown in this equation. You guys with me? So how would I do that? Theta 1 plus alpha is what? Tan minus 1 of 6/12. Somebody run that for me. Louder. 26.56 degrees. Okay, so if I knew alpha, right, then clearly I could get theta 1. Theta 1 is 26.56 degrees minus alpha. Okay, so that's an intermediate result right here. Once we get alpha, we can get theta 1. If I have this obtuse angle, that'll tell me theta 2 right away, right? The obtuse angle is 180 minus theta 2. So the point I'm trying to make here is, if I solve this triangle, the non-right triangle, I'm done, right? I can get theta 1 and theta 2 like this. Do I know 5 root 2, 5 root 2. Do I know the third side of the unsolved triangle? Louder? So it's the hypotenuse, right, of the dotted line triangle, yes? So I can write right here, let's put it on there. This is the square root of 6 squared plus 12 squared. Give me a number. That's root what? Root 180, right? 6 squared, 36 plus 144. So it's root 180. So I've reached a point where I need to solve a triangle where I know all three sides and I don't have an answer yet for any of the angles. Do you guys learn anything in trigonometry for how do I solve all three sides, no angles? I heard law of sines, I heard law of cosines. So I will direct your attention to the sheet. Okay? And there's a couple laws on here. The law of sines, the law of cosines. The law of sines basically says the ratio of the sine of every angle to the length of the opposite side is constant. So if I've got an angle, I can start using law of sines to find other angles, to find other sides. That's if I have an angle. Do I know any of the angles in here yet? Not yet. So all I have is the sides. So if all you have is the sides, the law of sines not helping you yet. But that's why we have the law of cosines. Okay? Law of cosines will give you an angle if you have three sides. Okay, and so, law of cosines, what does this look like? Okay, well, draw something similar to that. If I have a triangle that is a non-right triangle, okay, like this guy, and I have sides A, B, C, and I've got some angle here, we'll call it gamma. That is the angle opposite A. Law of cosines is like the Pythagorean theorem. Okay, and in fact, if the angle gamma is 90 degrees, right, then that would mean that a squared would be equal to what? B squared plus C squared. That's if it's 90 degrees. If it's not 90 degrees, I need a correction factor. Okay, and that is the law of cosines. That correction factor is minus 2 times the other two sides, BC, times the cosine of gamma, the angle opposite. Okay? 2BC cosine gamma. So that's it. So you can think about the law of cosines. I could use it for any angle I want. It's the Pythagorean theorem with a correction factor. Okay? And it recovers the Pythagorean theorem if you put 90 degrees, because the cosine of 90 is how much? 0. Okay? So I can use that guy to find this. So there's where we are. Okay? What angle can I find? Let's try and find the gamma. In this case, it's 180 minus theta 2. Okay? So here, the A is the root 180, right? Look at this picture. Look at this triangle. Okay, and so it's going to be root 180 is the A, that's squared, is equal to B squared plus C squared. B and C are both how much? 5 root 2 squared plus 5 root 2 squared minus 2 times B, 5 root 2, times C, 5 root 2, times the cosine of gamma. What's the gamma? 180 minus theta 2. So I have only one unknown in the equation, which is theta 2. Okay? So you run the numbers here, okay, and root 180 squared is just 180. 5 root 2 squared is 25 times 2 is 50, plus 50. All right, so I get 50 plus 50, minus 2, right, times 5 right 2 squared, this is 100, times the cosine 180 minus theta 2. Okay, and so I can do some math here. So I got 180 on the left, 50 and 50 is 100. Okay, and so if you solve for this, I'll get 100, right? 180 minus 100 is 80. Divide by negative 100, I get minus 0.8. This is the cosine of 180 degrees minus theta 2 is negative 0.8 is where I am. So, question for you. If I have an angle theta 2, okay, let's say this is an angle theta 2. Where's 180 minus theta 2? What quadrant? It's this guy here, right? 180 minus theta 2. So if that's theta 2, this big one is 180 degrees minus theta 2. How does the cosine of theta 2 compare to the cosine of 180 minus theta 2? Right? The cosine of 180 degrees minus theta 2, it's the same number but opposite what? Yeah, it's minus the cosine of theta 2. Okay, so I can replace this entire business with minus the cosine of theta 2 equals minus 0.8. right? And therefore, the cosine of theta 2 is 0.8. So somebody give me a number for that, and we'll call it a day here. Cosine of theta 2 is 0.8. Theta 2 is what?
36.87.
Theta 2, 36.87. That's an inverse cosine. Is that the only answer? When the cosine of an angle is a positive number, 0.8 is a positive 36.87 degrees the only possibility? I could have 2, right? Minus 36.87 degrees, right? This guy here, negative theta 2, has the same cosine, no? Positive theta 2, negative theta 2, cosine's the same number. 2 possible answers for theta 2. Okay? We will have to look at these 2 possibilities next time. We will see you then.